So two things. One is, I think I'm meeting with
That's your
Okay. Okay, done.
I know, I read your.
The second thing is this.
You were saying.
That is the but I don't know what to do.
16 days.
Like I have no application. I don't have application. Do you have any application for like Yeah, I can give you the okay. This thing on the we don't know what to do with it. And it's the fastest. Like so far, 7, maybe 8. We can do 12. We can do like reasonably a lot. No, because there's not a whole lot of theory. Like we can prove and buy. We don't know the conversion theory because of it.
Oh, you need of the morning? Oh, I don't know.
Shall we start? Yeah, I think we are ready. All right, welcome to the last session of the day. I promise it will be less equation-packed. So for us to continue slowly to the evening. Yeah, so my name is Mikhail. I'm from Google Research. And first I would like to thank the organizers of the workshop for creating such an event, and Simon's Foundation for hosting us today, and this entire week. So I'd like to talk today about graph foundation models, something that we've been working on quite a while, and what we achieved, and some glimpse on some new work that we are publishing those times. So some 4 parts, generally introduction to generalization problems. What are those graph foundation models? Why should we care about them? A few words about LLMs, because everybody talks about them, and some of the new work. So a few mandatory slides that graph mining at Google is working with very large graphs. And we are working, well, pretty much on all verticals of Google products. So everything where you're using some Google products, there is some sort of graph learning there, and there is some production graph learning algorithm there. And the scale of those graphs limits put certain limitations on the algorithms that we can use. And the range of applications spans from some very low-level system work to applications like with maps or YouTube. And in particular, our GNN team is doing a lot of work on enabling graph structure data inside Google, and we're focusing on several major areas like research, publishing papers, so doing some open source work, hopefully more JAX coming soon. We're working a lot on the infra and system level, and we do a lot of first-party models for different product groups. Okay, so after that, what are the graph foundation models? How they are different from language models, or maybe not. So that's the most important question for today. So yeah, 2025. As much as you would think that LLMs are everywhere, I will also say that graphs are everywhere. They come from lots of relational learning applications, from databases. We have a bunch of LLM reasoning. LLM reasoning, if you squint an eye, it's actually very much a graph learning problem. There is a lot of applications in coding, code graphs, and some big data sets for that. The whole area of geometric graph science for science, there has been a good amount of talks today explaining how there's a substantial amount of graphs there. There's, of course, social networks, recommender systems. They have been there, they will be there, because that's where the money are. And there is a lot of agentic systems, perhaps one of the interesting topics to keep an eye on. Yeah, so traditionally, graph learning focused on end-to-end training. So something that has been done 10 years ago and that people continue to do today is that given certain tasks, given certain data set, you would train some downstream model. So being at node classification, link prediction, or some graph level tasks, you would train a specific model specifically tailored for the features of this data set, specifically tailored for the classes of the data set, and maybe for some, even for some graph distribution of this data set. And then you would report a number for this. And the better your numbers are, the better is your paper, and that's how graph learning literature has been for quite a while. And we want to turn this around. Because it's 2025, guys. It's boring to run, to tune GNNs on particular data set. In fact, we want to embrace the amount of available data, structured data, semi-structured data that we have at hand, and we want to talk about foundational models. Those are models that learn traceable representations that can generalize to very different graphs and tasks. So what do we mean by that? Meaning that, well, instead of training separate models for separate data sets and tasks, now we have one single model that can do all the tasks, can generalize to very different data sets, to different features, different number of classes, and that is both engineering and scientific challenges, and some of them are pretty interesting to tackle. So some of those challenges are, well, you stumble immediately upon them. Something like heterogeneous features. So you have some data sets have bag of words features, some data sets have dense features, embeddings. Some datasets have no features at all. Sometimes you have numerical or categorical features. How on earth would you create an encoder that can be trained, say, on numerical features and can be generalized to categorical features? That's surprisingly unpopular area of work. We haven't seen that much work in that area recently. There is a bit more work on generalization, though. So we want the same model to generalize to very different distributions. Can be sparse graphs, dense graphs, can be homophilic, heterophilic classification data sets, can be link prediction tasks or graph level tasks. And generally, they require different levels of symmetries to tackle. So if you have one model for classification, say on 10 classes, can you make the same model run the inference on 100 classes? Usually you would expect, but I need a softmax head. How can I have a softmax head that trained on 10 classes generalized to 100 classes? That is an interesting practical problem. And then, okay, if I solve the problem and I can generalize from 10 to 100 classes, can this model then do link prediction? And link prediction can be considered, say, as a classification over the entire set of nodes that you have. Is it actually possible to do within the same model? So those are pretty interesting challenges. And yeah.
Just to be sure, when you talk about generalization, you're both thinking about generalizing to different tasks with the same graph neural network, but also with different structure of the graphs.
With different structures, yeah. That's pretty challenging, you see. That we're talking here, say, training on social networks and generalizing to molecules, for instance.
So why would you think this is possible?
Wait, because we've done that.
I mean, if you think about, I don't know much about how regular foundation models, but I have the idea that, okay, there's a lot of structure just in language, and that's what pre-training has. But in a general graph, what is somehow...
There are certain things about which I'm going to talk later, which enable some of those things. And then it becomes surprising that those things actually work at such small scale. So yeah, stay tuned. So we want to learn those transferable generalizable representations. We want to compute that we can use a lot of data and perhaps models of different sizes. And if we squint an eye, then we can actually see that there has been some first roots of the graph foundation models. And something that we published last year at ICML Spotlight, and there was a position paper at Look, graph foundation models are already here. And they popped out in first scientific areas, something like from the area of interatomic potentials. There the task is pretty generalizable. I think by the mid-2025, I think those interatomic potentials are indeed already universal. I can apply them for molecules, from periodic materials, and for all kind of chemical systems. However, we took it a little bit too extreme this year, and we went even further, and we say that, well, graph learning as a field needs graph foundation models to stay relevant. And this is another position paper which attracted quite some attention at ICML in Vancouver just a month ago. And we say like graph learning will lose relevance due to poor benchmarks, due to the problems how actually people try to position their papers since they can claim state of the art. And there we, among other areas where people should work on, as well, we think that people should work on to keep the field relevant in compared to, say, generative models for LLMs. One of them is to actually switch the setups for graph learning to foundational setups, meaning to measure actual generalization and how one single model can run on very different tasks and applications and graph distributions. So yeah, it generalizes and extends pretty much to all areas, to science, to databases, and LLMs. So I would invite you to check out some of the observations that we made in the position paper. Yeah, so some of the successes that enabled us thinking that foundation models are generally possible. I'll be covering two streams here, from link prediction and from node classification domain. First, coming to the link prediction, there has been a flurry of works based on some of our papers that we did a few years back. So the setup here is relational graphs. And we want to do link prediction on multi-relational graphs. And want to do zero-shot inference on new graphs at inference time. So you have new entities, you have new edge types. Usually, traditionally, you would build some graph embeddings that would be hard-coded to the set of entities, maybe set of edge types. You have a training, and then you would have to retrain it over and over for any graph. So you changed you added a new relation, you maybe added a few nodes, you retrain everything. So 10 years ago, it was okay. 2025, no, that is not okay. So the question is, can we have one single model that would be possible? What will enable us to run inference on any graph whatsoever, as long as it has more than two relations, more than two edge types? And then the main question, how do we get node and edge representations for graphs that we see at inference time and we have never trained on? And our task here generally is the ranking objective. So basically, given a starting node, given certain edge type, here it's some R1s, the green edge, we want to rank all the nodes as possible tails as a target of this edge. So it's a common task that you see in recommender systems, in fraud detection, and a bunch of other things. So some approaches that enabled us to do to increase the inductive level of those models is perhaps Neural Bellman-Ford is one of the most influential works. It's based on the idea of a labeling trick, and it sort of closely emulates the Bellman-Ford algorithm that given some query, you start from this head node that you have it as a query, and then by putting a certain indicator vector in it, it can be a different vector. It can be, there are several studies. What can this vector could be? In the general case, it can be vector of all ones, and everything can be all zeros. You start message passing process such that the final state of each node will be conditioned on the starting position. So what you have in the end here, every node would be encoding the conditional probability of this tail being a true tail given the head and relation. So that's actually pretty nice formalism, and it enables already inductivity in terms of nodes. So if you add new nodes to the graph, as long as it's a connected node, you can immediately get the score for it. So NBFNet is actually being published in 2021. It's still state of the art in link prediction on multi-relational graphs, even 4 years after. So that was really pretty influential work. However, the problem is it's still transductive in terms of that it still needs to learn the vocabulary of relations. And the idea of labeling tricks has been there for quite a while. It's getting, I would say, more traction, especially in the industry, because it's something that is pretty scalable. And the idea of those labeling tricks, specifically for link prediction, that, for instance, distance embedding from ICML 2020 paper, or something like that, that given node U and V, you extract subsampled neighborhood, and then you just label each node how far away it is from node U, from the source node, and from the target node. So it then gets, essentially you can only learn, say, the embeddings of those hop numbers. You can do the same for multi-relational graphs too. For instance, the node U would have, say, 0 hops from the node U because it is the source, and vice versa. And then you can label the entire graph like this. So those labeling tricks actually probably boost the expressive power. But there will be talk by Pablo tomorrow about expressive power of relational networks, and there will be far more content about that. So yeah, the question is, what are we doing with the new edge types? So we trained on one citation network. We want to transfer it to a different network with completely different edge types. So what do we do? The idea is that let's derive those representations on the fly, and for that we would try to build a graph of relations, the graph of edge types. So from the original graph of with nodes and edge types, we'd go to the graph where nodes are edge types. And the simplest example for that is just to look at certain topological structures. So for instance, if there are 2 relations starting at each node, we can put an edge between them. So in this graph of relations, we can just put an edge that somehow says that those 2 relations happen to have the same head node somewhere in the main graph. And there are only so few number of such patterns, 4 in this case, which generalize to absolutely any multi-relational graph. So as long as you have more than 2 different edge types, you can always build such graphs there. So here we define 4, but as we'll see a bit later that we can be a bit more flexible here. So with only those 4 graphs, 4 edge types, we can build representations for entities and relations on the fly, and only train representations for those fundamental, so-called core edge types. And that's what we did in our previous work as foundation model for KG reasoning, one of the first ones actually, that can generalize to absolutely any multi-relational graph that can solve link prediction on graphs of very different sizes from say 100 nodes to 1 million nodes. And the idea there is actually a 2-step process. First, given the original graph and a certain link prediction query, we built the graph of relations. And usually it's a pretty small graph, because even in the largest multi-relational graphs ever, you have like at most 1,000 different edges, meaning that your graph will have 1,000 nodes. That's peanuts. And then we start this conditional message passing process on this graph of relations to get representations of those nodes, and those nodes are actually edge types in our main graph. So we then just plug them into the original graph, and we use another conditional message passing mechanism on top of that. So in that way, we get the model whose parameters do not depend on the input graph whatsoever. So we don't learn any entity embeddings, we don't learn any relation embeddings. We only learn some function of topology, how those relations interact with each other. And that's perhaps the single most important lesson from this work, is that absolute information never transfers, but relative information, how features, how edge types work with each other, that actually transfers, and then we can learn this information. So practically, this single model, pre-trained on a bunch of standard graphs from here on the right-hand side, zero-shot generalizes better than the models trained end-to-end on many of those datasets. So we actually swept through 50-something datasets, pretty much the all existing datasets you can find in open source. And the bar here, the dark blue, meaning that this is just the zero-shot inference of a pre-trained model that has never seen this graph at training. It is in many cases better, and on average is 10% better than if you would train some embedding model or previous state-of-the-art model end-to-end on this graph. So this is the power of those transferable representations. You can fine-tune it a bit more, and then on certain graphs you have a much larger boost, but generally it will bump the performance a little bit more. So basically, the problem of generalizable link prediction on multi-relation graphs is very much solved. So we can do this pretty well, and it has all the properties of a foundation model. So you add more data, it works better. You increase the parameter count, that probably will work better too. Across different metrics, we see that across many data sets and across different tasks, some quality metrics grow. And then there is a flurry of extensions. I think over those 2 years, we've seen the extensions of this work to complex query answering, to different parts of different kinds of graphs, relational hypergraphs, hyperrelational graphs, temporal graphs, some text-enriched graphs, and so many of them. So that's pretty much, that was quite a successful project that enables us to thinking like, there is something to be learned from the idea how things interact. So it can be features, can be edge types. And there has been substantial effort to understand better the theoretical properties of that. Some of the recent work that we did with Pablo and it started actually a few years back also with Christopher on the paper Weisfeiler and Lehman Go Relational, so that we did back in for log 2022. And then it evolved slowly with a few iterations through Europe's 23 work on theory of link prediction through relational Weisfeiler-Lehman to the very recent ICML work on expressiveness of those knowledge graph foundation models. And since we started motivating of those models through how they capture those relational patterns, the main idea there is to look actually, are there certain patterns we cannot capture? And in fact, yes, there are some. In many cases, actually they do happen in real world graphs too. So our model, the first version of it, for instance, cannot capture the difference between if the node uses start and v1 and v2 are target nodes, then this model will treat the representations, will treat them essentially as automorphic. So it will not understand the difference between this R1 and R2 over those target nodes. So that's something that we can fix by introducing harder and more complex motifs. That's actually the name of the whole framework, became a motif. So instead of just say binary relations in this graph of relations, we can be more creative and introduce more complex patterns. Can be like 3-path motifs, can be a 4-star motif, can be motifs actually of arbitrary complexity. And there what we show is that if you increase the complexity of those motifs, you get probably better expressive models, which works better on theoretical benchmarks and on practical level too. So if we look at the representations of the relations that the model gives us and their cosine similarity, then we'll see that considering more higher order relations gives us more distinguishable representation. So in the original model, all of them are very close to 1. That's how we can actually, it's quite a avenue to increasing the performance too, to make them less similar. But so this work actually makes them less similar, and we see some better performance. So yeah, we can derive a hierarchy of increasingly complex patterns from 3-path motifs to 4-star motifs, and they get us to better representations of relations. Alrighty, so after that, some news on generalizable node classification. There, in node classification, what you usually have is some node classification data set with different number of classes with different input features. And several important symmetries to keep in mind is the feature permutation variance. So if you just swap columns of your node features, the result shouldn't change. If you change the order of classes in the class labels, then you should, the predictor should change appropriately. And if you swap rows in the node feature matrix, then you should swap labels too. So those are 3 main symmetries here. And in the iClear 2025 work, we introduced GraphNE. So this is the first inductive node classifier. So it can do pre-train a single pre-trained model. It can do classification arbitrary graph on arbitrary number of classes. So literally, our task was we wanted to train a model on core and generalize to everything in PyG, even though it has like 100 classes or 1,000 classes. So here, the setup is pretty straightforward. We have some pre-training graph. It has some number of features and some number of observed labels. we train on this set of labels, and then we want to generalize to absolutely different graphs with a different number of features and different number of classes. And that seems a little bit non-trivial to say, like, do we want to actually play around with softmax and some feature preprocessors? And so far, the literature was revolving around, say, freezing the backbone GNN and then maybe training dataset-specific feature processors and pre-head. But we don't want, it's 2025, we don't want to tune those things over and over again for each dataset. I'm a simple man. I want just to run model forward and get the predictions. And don't care about fine-tuning all the time. So the idea here is to use linear GNNs and actually to learn a function over predictors that already give us certain label distribution. So we are bypassing here the problem of learning representations of nodes. And what we do is that given any starting graph, we would first run a bunch of linear GNNs, can be powers of adjacency, for instance. And since they are linear GNNs, we can compute for them pseudo-inverse analytically, essentially through least squares. And we compute this pseudo-inverse on labeled nodes. We apply this pseudo-inverse together with the given node features to nodes that we want to classify into the target nodes. And we stack those predictions and compute pairwise distance between those logits. And applying certain tricks and like entropy normalization and learning some attention functions. So the entire learnable thing in this model is a small attention matrix. So it's pretty tiny. It's like 100,000 parameters, even smaller. And it's essentially we learn to reweight predictions of linear GNNs to prefer, say, homophilic or heterophilic interactions, and give the final prediction on any data set on the fly. So it has pretty good transfer capabilities. So indeed, we train model on a bunch of different existing data sets. You can train it on one, you can train on 5 and so on. So like training a model, a single model on the Wisconsin, which is like 100 training nodes, or even smaller, we can generalize to the entire suite of PyG data sets. And we can do it better than if we train those standard GNNs from scratch on each of those data sets over and over again. So zero-shot generalization to all of those data sets with a very different number of feature dimensions, up to 4,000, and to the very different number of classes, to see, from 3 to 200. The same model can do it better than if you would train a specific GNN on each of those data sets end to end. And some of the numbers to prove the word. So here on the left-hand side, those are linear GNNs that show the best performance if you train those, well, use those predictions on each of the target data sets. So for instance, say archive, Quora, and full Quora, they like homophilic interactions. So if those homophilic GNNs would show better performance. And here, if we look at the predictions of graphene, actually on the weights that this learned attention produces, then indeed on data sets which should prefer homophilic interactions, they weight predictions of homophilic or higher order powers of adjacency higher than heterophilic interactions. So there is indeed some interesting signal inside of those models. And recently started to see more extensions of that. So another recent work called Equivariance Everywhere All at Once. I like the title very much. So they are I think they propose a little bit more principled approach to capturing those symmetries and to train those generalizable classifiers. A few words on challenges. So shall we still work on in the future, maybe in the next year or so? In the featurization, there is no single feature space. So, oh yeah, the question.
So you have a model for link prediction
Yeah.
and another model for classification.
Yes.
Will you have one model that does both?
That is where I'm going to.
Okay.
Yeah.
Curious about as you do the node classification foundation model, is that model go beyond the conventional label propagation scheme? Because basically you do not train anything in your GNN layer, so we can survey that you only focus on how to mapping maybe the feature space to the to the label space, and
Yeah.
everything is just follow the conventional label propagation scheme, and they do not do any kind of filtering or the importance measurement during the aggregation process. Is that correct?
Yeah, that's correct.
Okay.
Yeah. And the problem why it's hard to devise representation learning mechanisms is the function that would map from input features to some latent space.
But based on the injective property,
Yes.
you have to do this.
Yeah.
Okay, I see.
Alrighty, so some words on the challenges. No unified feature space. So there is no notion of tokens as you would do in language, or say image tokens, language tokens, audio tokens, something that can be fed in language model. We don't have that for graphs. Well, unless you use some motifs and some decomposition, but that's kind of old and doesn't scale. So each data set has its own feature and label space. And in the OGB, there are data sets with very different number of features. No single vocabulary. If you want to train a foundation model, you need a unified latent space. Actually, if you want to have a representation learning method, not just a mapping from one space to another. And cross-task generalization seems to be a problem too. So if you train a data set on node classification, we know in some general ways how to generalize to a different node classification data set, but transfer it to link prediction, that seems to be a pretty interesting task. So some of the work we did at Google for that. For foundation models for relational data. It's something that is relatively fresh off the press, that we published it right before ICML, foundation models for relational data. And there, our setup is a bunch of relational databases, and can be many of them, can be on the order of 100, for instance. And we want to have a single model that would perform different tasks, node level, link level, graph level tasks on those relational databases. And we can use the graph inductive bias from those connected databases. First, the rules of transforming tables to graphs are pretty simple, where each row becomes a node, the foreign keys become edges, other columns, which are not foreign keys, those become node features, can be categorical, numerical, Boolean, whatever. And each table becomes its own node type. So this is a standard conversion process where this is how you would transfer a bunch of source tables into a connected graph. And the idea behind the graph foundation model is that we can train it on a set of input tables, say in classification task, and run the inference on completely different graph, on completely different set of tables from which we get a different graph, and run a different prediction task altogether. Can be regression, can be link prediction, can be something else. And it can run it in a zero-shot fashion. So there is no need to fine-tune. You can just slap a pre-trained model on whatever relational graph made from tables. You have it inference, and it will produce predictions that in many cases better than if you train a neural net from scratch. Yeah, I've heard some positive feedback about the quality of those charts, how expressive and visual they are. But yeah, basically, we get significant performance improvements from using graph inductive biases, essentially by converting tables to graphs, compared to best available single table models. So something that is state-of-the-art in the literature, state-of-the-art that works in production, something that can be found in open source. We find that just using graphs on connected tables brings us a lot of improvement, on the order of up to 40x better, which is pretty much a step change. Some tasks that weren't even possible before, when now we can solve them pretty well. And those here the tasks are some spam detection, node classification, something that would help us to prevent some abuse with spam in ads. So some lessons learned from that project is that, well, indeed we can have one model that would do all the tasks for us, node, link, and edge level. The question is, perhaps the most important component there is that we need to learn meaningful latent representations, meaning that we need some representation learning methods and ways to convert those different graphs and features to the same latent space. The absolute information doesn't transfer, relative encoding transfers. That is a very big hint on the algorithms that you can use for that. We can leverage scale both for the model and data size. So actually, it's pretty unlimited. I can say that the more data you have and the beefier models you have, you can encode quite a lot of information there. And well, especially specifically for running those in production, you need certain efficient algorithms for training and inference. And I'm talking here about kernels, about some very effective implementation of graph learning, of message passing on hardware. And that can be another 1-hour talk on those efficient implementations on kernel level. But that's basically an important part of running those things in production on very large graphs. And yeah, still have plenty of time. The other side of the coin. Oh yeah, questions?
I have a question on like what kind of tasks do you do with this relational data? Like, can you solve queries? Can you answer queries? Because these are relational tables that you're dealing with, right? Relational data. So, what are the tasks?
Well, the task is going back to some of those tables. It can be deriving classifying certain row, a certain column of a certain row. If it's a categorical column, then you want to predict the value of this column. If it's a numerical column, then you want to predict a regression target, like some numerical feature.
She was asking about, let's say, a join or something.
Yeah, join query or something. Can you do something based on that?
Yeah.
What kind of things can you do?
Aggregations, some multi-hop predictions. That's actually what makes it better standing out from single table-based lists, because they will usually tabular ML methods only work on a single table, and you have hard time stitching the predictions of two tables together. And here we are getting that out of the box. So we can answer pretty complex SQL queries and other relational modeling tasks here. Yeah.
How should we think about these tables? Are they generally 2D tables, or like the 3 and 4D kind of more complicated, high-order relationships?
The features themselves are, the values for them are scalars, meaning that we have in that sense, we have 2D tables. Vectorial features, sometimes you see them. Yes, can be, for instance, like embedding vector from an LLM, which serves as a feature somewhere. That is.
But the tables themselves are fundamental 2D, so the rows and columns. So it isn't like a field.
Yeah.
I'm curious about what is the pre-training under a context of the graph foundation model, because basically you talk about tokenization, right? But okay, we can say that we can use node, motif, or age to do the tokenization, but the leap of the language model are basically based on we have a lot of corpus for pre-training, but for now, even though we have shown some inductivity, but they have been studied before for graph attention network or the graph convolution network. They are also showing similar applicability on training on one graph and the inference on another. But what is the pre-training, which is very, very fundamental for the large language model? So how do we define the pre-training under a graph? Because basically we only train on the graph. We don't have the shared corpus or shared knowledge for among all the graphs.
Yeah.
Right? Yeah, so is there any kind of the potential direction, or
well, those are all self-supervised methods in the same way as language modeling is a self-supervised task that you reconstruct the original sequence with the position, with the causal mask. And for graphs, for featureized graphs, like those graphs, you can envision a bunch of pre-training tasks that you can do at scale.
But there is no distinct kind of the shared corpus for all the graphs to do the pre-training.
Which corpus?
There isn't a corpus for this stuff, right? For this text, right? For the pure pre-training, such as a wiki text or the Reddit for pre-training a large
Actually, I think recently Kaggle and a few other resources, they put up quite some hefty relational databases to train those models on. They are on the order of like millions of rows and hundreds of features. So if you can transform them to graphs and have a look, you can have some fun with it. Yeah.
I have one more question. So how big is the blow up of this graph when you're converting from like tables to graph itself? Does it blow up too much, the size?
Well, no, because generally the number of nodes in this graph is equivalent to number of rows in your table that had.
Got you.
So if you have 100 million rows, you'll have 100 million nodes. Well, maybe unless you add some additional heuristics to make those rows somehow better connected. If they share certain other features, then you can introduce some virtual nodes or something else. But generally, the order will be on the linear with respect to the number of input rows that you have in all the tables combined.
So there is one thing, like I'm from the theory community, so there's this thing called relational algorithms, which is kind of new, where you take tables and now you don't compute the joint result because it can blow up, but you want some like clustering on the joint result without computing the joint result. Can you do something like this with?
Oh, that's actually what representation learning is used for, yeah. You can absolutely do that in latent space. Yeah, any more? Was there some other question? Yeah.
So I'm also trying to figure out what it is that you can what information you can possibly transfer between these different tasks. And I'm wondering how, in the baseline, what form you would learn from these tables. In particular, like one thing that was discussed earlier, that in the graph neural network, message passing in particular, automatically captures the invariance. In this case, that would be invariance with respect to the ordering of the rows and the columns of the tables. So is it possible that that's really what this graph neural network connection picks up on? But if you re-represent your tables as a graph, then at least that part is sorted, and you have a strong bias towards learning relations that don't care about the ordering of the...
No, nothing is ordered here. They are absolutely permutation and invariant here. Yeah. What is being learned? Well, the connectivity structure between the rows. So that's something that single table tabular methods, chart XGBoost and some others, they cannot do. But something that you can almost get off the shelf by transforming those tables to graphs. And suddenly rows and tables become more connected. And even though you don't have labels for some of those rows, still this connectivity information helps a lot. Even in whatever downstream or self-supervised or downstream classification objective you have it. Turns out it is much better than treating single tables as is with the best baselines. Yeah.
Sorry, one more question if you have.
Of course.
Initially you were talking about this, when you were talking about link prediction, you were talking about, kind of representations that you're getting. And you're talking about motives, right? So I work in subgraph counting. Have you used that, like count the number of triangles in the graph? That's kind of something, it gives you some information, right? So can you use that to encode some information here?
You can use it as an additional feature. If you have a scalable method to compute some approximate value of it on very large graphs, it can be one of the features. Is it the most crucial feature? No.
So this is not related to your relational databases. In the previous slides when you're talking about link prediction and the classification. So you're talking about how your models generalize across domains and you've tested it on like a variety of data sets. So for the training data, did you have data that was already in graphical form, or did you take text data, convert that into graph? Like how did you get the training?
Oh, here the source data were relational databases.
In your previous
In the previous work, yeah, those are existing data sets in the community that have been they can find in open source libraries off the shelf.
Okay. Have you tried turning text data into graphical form? And
Yes, I'm going there. That's actually the second part of the talk. Yeah, I'll go there then. going to exactly following your request, large language models as some interesting possible candidates for foundational models. So you can argue that, well, GNNs are cool, but what if we actually start to use gradients of, or just use some inductive bias of language models? Because we can generalize going from GNNs to LLMs and actually add graph information to language models. And there are so many approaches for that, and one can argue if they are really introducing something new. At least some of the approaches, listing them here, something that we published over the last few years too. The most basic approach of representing graphs for suitable format for language models is expressing in text. That seems a little bit, though, maybe not very effective, because it's very similar to expressing an image in text. Instead of just setting and whatever PNG or just an image, you'll be describing that there is a bird sitting on a tree somewhere, and the sky is blue. Like you cannot convert much information from it. So there has been several works measuring how well can you transfer the graph information in text and whether LLM can pick that. And often, for some small data sets, yes, but it certainly won't scale. You very quickly will run out of context window for anything remotely similar to production workloads. Far more interesting approaches, though, is the use of tokens. So this is one of the recent papers called Graph Token, is that where instead of representing the graphs as text, we would actually represent them as soft tokens. And we would train just the token, keeping LLM weights intact. And then we can query those soft tokens in a similar fashion as you would query, say, image patches in VLMs. And that suddenly works on a variety of applications that can remotely use graphs. Starting from the Talk Like a Graph paper. This one looks on the first, more basic level, like we would first encode the graph as text, and then we prompt it in a very straightforward fashion. Like here we just describe a graph as is, and we ask the question, what is the degree of this node? And the first versions of this work show that, well, if you use better, fancier models, then suddenly you have better performance. Well, is anybody surprised here in 2025? No, we could probably expected that. More interesting is that you can use representation learning method and actually turn them into soft tokens. And that will be the graph tokens, graphs that talk. That was another recent iClear paper that now we can actually learn a joint latent space between graphs and LLMs and send those soft tokens to a frozen language model. And then it's actually up to your fantasy what you can send there as the original graph. Some of the applications that we used, it was, for instance, predicting the runtime of deep learning models. So you have, say, a configuration of a JAX program. It's usually a computational graph. And you want to predict the performance, how fast my kernel is, how much compute would I need, what are the memory requirements of this kernel. And surprisingly, it actually works pretty well. So if you turn this graph into the latent space suitable for a language model, then suddenly you can query those configs pretty effectively. Here, in the absence of the tokenizer, we would use the tokenizer is a usable language, but since we have very different components, very different modules, can be in JAX, it's all the entire world of building blocks and differentiable computing. So we want to express very different graphs of computational workloads and send them to language models. So the graph token there is very useful. And we could use their, standard GNN architectures, but now feeding those representations to frozen language models. So an important part here is to actually keep those gradients flowing well, because, the question.
Sorry, what is the graph token thing outputting? Is it like an embedding that represents the graph?
Yeah. It can be one, can be several, depending how you pull it. But the thing is that it immediately will be as a plugin token in the space of a language model. So yeah, the important takeaway there is that you have to keep an eye on the magnitude of those weights. Because some language models, especially in the open source world, if you just try to fine-tune them a little, you immediately like put the magnitude of 100 on your model, and you very quickly squash the entire signal by very large gradients. So that perhaps an important lesson, to keep those tokens generalizable such that you can train it for different language models. Yeah.
Do we need to impose some constraint between the prompt tokenizer and the graph tokens? Because sometimes, for example, the prompt could have some information that needs to be conditioned on the graph, but from the diagram you're showing, it seems like they're two independent modules.
Well, yes and no. Well, I would say it depends on the task that you want to solve. For instance, if you want to have some ranking objectives, then perhaps you would want the content of the graph and text to overlap somehow. If you're solving more point-wise objectives, like single point classification regression, then just some starting latent representation is better than starting from a random point. And and some encoders can already give some good starting point for the optimizer to work out the LLM gradient. Yeah, going forward. Oh, yeah.
Do you really need the language model? I mean, it could be any deep learning architecture, right? Do the language model really provide the crucial benefit?
It's a nice interface. If you can just talk to your config or write an LLM without the need to do additional conversions or getting some sort of textual representation for this data. It can be like a pretty hefty log, which will be very hard to stick into the context length of modern language models. And with a bunch of soft tokens, you can compress quite a lot of content there. Yeah, so some initial experiments on that say it's actually it's an efficient representation method. It's better than expressing things in some structured formats or unstructured formats. And we can reliably, well, to the extent, predict the performance of those kernels already. And I have still some time for the few words about some new work. So hopefully now you're excited. Yeah, graphs, LLMs. Yeah, probably there is a path for them to work further. So here we ask a question that can we go one step further, and what instead of having LLM over graphs, we can have graph of LLMs. See, that is a wonderful abstraction. We can go even deeper. So now let's look at the setup where we have connected language models connected into a certain structure, a certain topology, and we are interested: can they work together efficiently to solve certain problem? And something that we released very, very recently is the paper called AgentsNet. It's the benchmark for multi-agent systems, for LLM agents, how they can talk to each other and can solve certain pretty basic problems from distributed computing literature. So we measure their coordination and collaborative capabilities. And the basic tasks there come from standard distributed computing courses. So every node in our graph is the LLM agent. You can connect them by APIs or by some other agentic frameworks. You impose certain structure on them, and then you ask them to communicate, to talk to each other, to solve some basic tasks like matching, some vertex color, or consensus. Consensus, for instance, is the most basic one, so they have to agree on a number. You seed them with some random numbers, and you ask them to talk to each other in several steps. Can you guys agree actually on one single number? It can be a number from any of them. Can they cooperate, or they will be refusing to work with each other? That's pretty interesting. Yeah, the question.
Oh yeah, so you can do like Paxos graph or something on top of this. That's what you do in consensus. Like in consensus,
Yeah.
right? So you do like Paxos or Raft kind of thing on top of this? Like consensus protocols, like distributed consensus protocols?
Well, that's pretty basic here. So when probably if you squint an eye, then probably yes. But right here we would just ask them to. The protocol is synchronous and they talk to each other, and so far nothing else. No more bells and whistles on top of that.
Okay, but you don't use LLMs for the consensus itself. Like you just use the LLMs, represent the LLMs as graphs.
Mm-hmm.
For the task itself, you don't use LLMs.
Well, the task for LLMs to actually talk to each other and agree. Let me actually go to the example. So here, one of the data points where we have a network of 16 agents. So each of those points is an LLM, can be an LLM, from the open source LLMs to some frontier models. And we question here to solve, actually don't remember which task here, but they talk to each other in steps, in synchronous steps. They have a starting prompt saying like, your name is like this, and your immediate neighbors are only those 2-3 nodes. And your task, for instance, is to select the color such that your color will be different from the color of your neighbors. So some basic graph coloring task. And then they start talking to each other, and then we can see if they cooperate, if they not cooperate, if they ever start to build their understanding of the network where they are located or not, or they just stick to whatever random number and transmit it throughout the whole message passing step. So we do message passing here. It is done by exchanging messages through APIs. And LLMs themselves produce the final result, which we then only record and compare whether they satisfy the problem or not. So the LLMs must have produced the final result in the end, which is like selecting a color or agreeing on a number or something else, some one of those five tasks. So LLMs do here most of the compute.
Do they also have memory?
Yes. Well, to the extent of the entire history of message passing steps. So here for this graph, which has say diameter of like 5 or 6, for certain tasks we would allow them either the diameter amount of steps or twice more, to fully exchange messages from any two nodes. And they keep the history of the entire message passing between them and all their neighbors, if they send them. Because in many cases we found that actually some of the agents are not very cooperative. That's actually what I'm coming to. So that I basically explained. So some of the interesting results we found is that all of the models are pretty good at solving basic consensus tasks. But then when it comes to harder things like vertex cover or coloring, then only reasoning models can do that. So what we found looking at the logs is that those models actually do start building some understanding of the network where they are. And they start working with their neighbors to understand to understand who is next to them, what is the size of the graph. So what is the network they are in. While smaller models, they just pretty much refuse to cooperate. And in many cases, we've seen the logs that say, like, oh, the task is too hard, I'm not going to work on it. So I'm just sticking to whatever number I have, and I'm not going to do anything else. So we found that some thinking models, some reasoning models, they're not solving the tasks completely, but they are generally more effective in harder algorithmic tasks. And if we increase the size of those graphs, of the number of agents, then we see that performance quickly drops. So generally, this is a good part of the agents net is that so far is the largest benchmark in the literature on the number of agents. So if you look at the data sets for multi-agent interaction, it will be on the level like 4, 7, yeah, maybe sometimes they scale to 10. Let's say, well, let's slap 100. And actually, we have evals for far more agents, but there'll be only a few models that that you can query in those amounts of agents. It's mostly infrastructure problem of tokens per minute and tokens per second that LLM endpoints can process. So basically, we scaled those setups, those graphs to hundreds of nodes. So each of the nodes is an LLM agent. And we have different distributions of those graphs, and we ask them to solve those tasks. So those are aggregated numbers across the tasks. And so far, consensus seems to be like still in the reach, but other problems, they fall off in the performance pretty fast. So that is still a very interesting thing to study further. Can we have what kind of knowledge those agents must possess in order to solve those tasks despite the size of the network? Because in the end, what we want to have in those networks is for them to be independent and to not have any hub node that would talk to them, what would say them what they should do. So basically, you remove one of the nodes, they should still continue to solve their task. So nothing can break it. So it's a peer-to-peer communication without hub nodes. We specifically on purpose went against hub nodes here. And if they can dynamically reconfigure the network if something goes wrong, then that's something that will be very interesting to study. Yeah. Mm-hmm.
So you could do multiple talking between the different agents in this setting that you're describing.
Generally, you can. Yeah, it's only limited by the infra you have at hand for querying those. Right now,
But you don't have any analysis for example, the number of the message passing or rounds of the communications and the relation to the structures of the graph.
Well, so we don't, because we have those predefined for starters. It's a configurable thing for designing new tasks. For the sake of having some results we can aggregate, and for all of those tasks, we fix the number of message passing steps. Well, it can vary depending on the complexity of the task and the size of the graph. It becomes bigger if your graph is larger. And we just make sure that there is, even in tasks that require full communication, the message can travel from the starting node to the furthermost and then back. So it's twice the diameter. Another important factor for those multi-agent systems, we want to scale them really to the swarm sizes, to hundreds and thousands is the price. And so far, we see that in many cases, there is a very noticeable Pareto curve here. So surely with the novel models, it will be moved slowly to the left-hand side. So we'll be able to solve more complex tasks with more agents cheaper. And at some point, we want to make them economically viable, such that we can be able to control large networks in less than $1, essentially. That would allow us to build pretty cool pipelines, I would say that. Yeah, so the website for that is openly available. There, in addition to all the data points, you can actually play around with the logs. So we recorded a bunch of interactions between the models and in different setups and different configurations, how they talk to each other, how they refuse to talk to each other. Some of the models that allow tracing the reasoning steps will also we can also publish those reasoning steps, and then you can see that some of them get, say, distracted by very short-living context. Some of them actually stay on point to solve the task. So that's pretty interesting. That's something that we definitely want to continue working on. Yeah, and I think that would be concluding the talk. I will say that we're also looking for student researchers always. So if you know someone, just send us an email. Yeah, that's it. More questions? Yeah.
It seemed in this last slide you mostly showed problems that got harder as the graph, or as you added more agents. Like, are there problems that get easier as you add more agents? Like, are there things where adding more makes now you can do more according to more? Is it always in this direction, or? It's
most always in a single direction. Yeah. Otherwise, you can argue like, why should you care about those problems that get easier when you have more agents?
I guess I was thinking like, the reason you have agents in the first place is because presumably it can do something for you, right? Or you just have one. So you're adding more like coding agents or something to the problem so you can do something easier than you could with one. So.
I would say the biggest difference between AgentSnet and those existing multi-agent frameworks is that existing frameworks are a lot tree-based. So you have a hub node that commissions a bunch of sub-workers to do certain stuff, and they return back the unit of work back. And here it's actually distributed network. So there is no hub node which would say like, go to search, find this thing, get back, and then he would send this to a whatever coding engine or image generative model to get some other piece of work. Here they actually have to communicate and work together to solve something. That is, for us, that was one of the interesting motivating factors to work on the problem, which would go beyond those typical tree-based topologies. Having said that, I would say the reviewers actually ask us to run experiments on tree-based topologies. We said like it will be done, the reviewers, but they insisted, so yeah, of course we have to comply.
So I'm a bit confused about the definition of the graph foundation model. So you have this like graph representation, and then you have the link prediction and the node prediction.
Yeah.
Are those part of the graph foundation model or just the representation of the graph?
Well, we can call them proto-GFMs. In the sense that they're still not generalizable. We're still far away from having one single model that would solve node classification, link prediction, graph classification, regression all in one model. But they solve generalizable problems in their domains. So everything link prediction done, everything node classification possible. The next frontier is to merge those things together.
When you say everything link prediction done,
yeah.
Like what do you mean with that?
Say link prediction on relational graphs. So running some recommender system tasks on the graphs that have more than one edge type. Now we can do it zero shot on every possible graph whatsoever.
But you need to define what is a link prediction task beforehand, right?
Well, yes.
You could have several possible ways of link prediction.
That is true. Yeah. You can frame link prediction as graph classification if you want so. But, there are still ways to do that. Actually, some of those, so going back a lot over here. Yeah, so for instance, a lot of the papers that worked on the labeling trick, they, for instance, you can treat this link prediction problem between those two nodes as a graph classification. So you label the nodes, you run message passing, and then you pull the information from the nodes, and it's a binary classification, whether the link exists or not. So is it a viable formulation of a link prediction? Yes. Is it always the most useful one? That is the question. It's probably a question of downstream application and scalability that you want to achieve. So let's say papers from 2018, 2020 that first introduced that, they used the sort of a graph use it as a graph classification task, but then it always becomes a hurdle scaling it up because you have to do a lot of subsampling around those nodes, and then there is some infrastructure problems. If there are ways to do it more scalable and faster, then it will stick around a bit longer. The same way you can frame link prediction as node classification too, or node classification as link prediction. That is still possible. If you introduce, I know in some of those graphs. Yeah, let me go here. So for instance, if your nodes are typed and you have node labels, you can just put the nodes representing labels in this graph too. And then you can, instead of running the classification over some set of nodes, you can frame it as a link prediction, like whether, for instance, this node it has an edge to some of those class nodes. And then you can frame node classification as link prediction. And it becomes an interesting exercise. Like you can represent every task through every other task. And whatever you like more, that you would stick to.
Yeah. I'll ask you offline. Thank you.
Mm-hmm.
Yeah. So back to the agent graph. how the degree of the nodes changes as the number of agents grow?
Well, it increases. The graph distributions generally that we use here, they aren't random graphs, but those are we use 3 different distributions. So yes, the density will increase, but then diameter will increase too. Those are all well, we can build histograms essentially for all of them because all of those are fixed data points in the data set. But generally, yes, the graphs become harder, larger and harder. Yeah.
Yeah. So because you're looking at this distributed network, right? So can you imagine, like, for distributed algorithms, usually in each node you break a graph and store it. Do you do that here, or no? It's just like the graph that you're showing.
That is a wonderful question. Do we have to stick to the topology, or we can bypass it? So far, we stick to the topology. Some agents might decide not to send any message, so there will be some edge will be dropped at certain time step. But they have an option to do that. But can, for instance, this node can send a message to the node which they're not even aware of, only if they ask their neighbor to transfer.
Got you. Okay. And like the graph that you're dealing with is the graph that you're seeing right now, right? So my question was, like, if you have a really large graph that you want to store on different nodes, so that's basically distributed graph algorithms, right? Can you do that using this? So for example, you have this distributed network that you have LLMs on, and I have a really large graph that I break and give it to each LLM.
Well, that's the whole point. We don't prompt LLMs with the entire graph. They are only aware of their one-hop neighbors. So there is no notion of a complete graph until they build it themselves. So here we, as evaluators who design these tasks, we have this network for evaluation purposes. But what each of the LLMs has at the very, very first step when we prompt them is there are only one-hop neighbors. And then it's up to them if they want to reconstruct the entire network structure or they do not need that. So in that sense, it's infinitely scalable because you can only it's only enough to let LLMs know about their immediate neighbors, and you don't have to encode all the 1 million node graph for in the context line. If they want, they can receive. Well, usually it's what's happening in the first step for reasoning models. For instance, they immediately ask who are your neighbors. That's and then in a few steps they reconstruct the networks, and that's what we see in the numbers. Why some of the thinking models here, especially on larger graphs, say on 8 nodes, they are much better than non-thinking models, because that's in the very first few steps out of their budget of steps, they can reconstruct the network structure. Oh, so many questions.
So why jumping to LLMs? Why not just try this first for GNNs? Like I have pre-trained GNN models, and you make a graph out of them, and they can communicate.
That's 16 nodes. No, that's too tiny.
Too tiny.
Yeah, too tiny.
Because they probably also can solve these problems.
Yeah, well, that's what the reviewers asked us too. That in the updated version, we'll have results how GNNs can solve it. In many cases, they can solve it ideally, perfectly. But that's not the whole point of the work. The whole point of the work is to let LLMs communicate with each other. And there has been, perhaps the interesting part here is to measure the agreement of them, if they can cooperate. In GNNs, nodes are cooperative. Only if we talk about unless we talk about cooperative GNN paper from last year. With LLMs, you cannot guarantee they'll be talking to each other. And that is interesting. Yeah.
I had a generalization question on where you're inputting the graphs into the LLM. So you're learning now the graph embedding, I guess, targeted to the LLM.
Yeah.
How generalizable is that particular graph tokenizer across different tasks? Is it specified to the task you train it on, or would that now work on other tasks?
Yeah, that's a wonderful question. I hope we will come back with a more principled answer to this in a paper in a few months. Generally, it's pretty promising. The answer is yes, it can generalize to tasks you didn't train it before. So, for instance, if you're training on some easy task like on the diameter of the graph, can you predict then the average degree of each graph, of each node in the graph? Yes. And why it happens, we have certain ideas on that. That's a wonderful question. Thank you. Yeah.
I'm interested in that because we are talking about foundation model,
Mm-hmm.
but I think there's a bunch of the theoretical papers that focus on we are investing more comprehensive operator embedding space or a lot of stuff to make the GNN more expressiveness. But when we talk about the foundation model, it seems like we are really focused on really simple model architecture. So it doesn't indicate that if we have enough data, then we don't have all this theoretical stuff. We just have to train it and get the final result, and somehow it will be correct.
Yeah, well, in many practical cases, one WL is enough.
Okay.
That's the sad life of the industry life. You have the graph structure and the feature distribution in a way that very simple baselines already work pretty well. And that's why deep walk is still pretty effective, actually, on many recommender system tasks. It's a question of making that scale and use compute better. So I'm actually, it's a nice but long segue to Hannah's work on this. Always, like it's a rant about whether you need equivariance versus augmentation, and people who like compute, throw compute or work more on the data. It seems that GNNs can benefit from compute too. There was? Yeah.
I think I'm fine.
Okay.
Got the answer.
Yeah, that's so boring, I understand. Alrighty, then it's the end of the day. Would like to close the day and let everyone go for dinner?
Yeah, that's it for today.
There is a reception today.
There is a reception.
Oh, there's a reception today. Yeah, thanks a lot. There's a reception at 5 o'clock. Yes. Thanks, Andrea. Outside here. Oh.
Don't go, don't go.
So reception starts in 10 minutes.